Hello and welcome to this section about the periodic table that deals with the mixed groups. So there are groups that have metals and nonmetals, or metals and metalloids. We're going to look first at properties of metalloids. Then we'll take a look at the boron group, then the carbon group, the nitrogen group, and the oxygen group. You already know some properties of metals. They are shiny or lustrous. They're malleable and be hammered into a shape, even a flat sheet. They are ductile, can be drawn into a wire, and they're good conductors of electricity and heat. You know, properties of nonmetals are the opposite. They lack all of those things. What about metalloids, these elements in the middle? Basically, they have some of the properties of metals and some of the properties of nonmetals. For example, some of them can conduct electricity a little bit, at least better than nonmetals, but not as well as many metals. So they're sort of in between the metals and the nonmetalloids, possessing properties of each. Let's take a look at the boron group. It comes from the periodic table right here. And here I've magnified that a little bit. Boron is a metalloid. You find boron in compounds like borax, which is a water softener in laundry products, in some laundry products. Boric acid also contains boron. It's a mild antiseptic. Boron is also used to make heat-resistant glass. It's added to the glass in your lab beakers, for example. Aluminum is the next element in this group. It's the most abundant in Earth's crust, actually. It's the most abundant metal. It's really strong and light, and so it's used in, obviously, aluminum foil or soft drink cans, bicycle frames even, and airplanes. Gallium is a metal that is used in some electronics, and these two metals here, indium and thallium, those are very rare metals. So what do the elements in the carbon group have in common? Well, they each have 4 electrons in their outer energy level. You can see here is the carbon group right here. We know that there would be 1, 2, 3, 4 electrons in their outer energy level. That's about all they have in common. Carbon is a nonmetal. Silicon and germanium are metalloids. And tin and lead are metals. Let's take a look at carbon. Carbon is a nonmetal, and it occurs in many, many, many different compounds. It occurs in natural gas, oil, foods. It's in CO2, carbon dioxide, and that is used by plants to make food. Carbon compounds are they make up all of the different macromolecules in biological organisms, and all organic compounds, in fact, contain carbon. However, not all carbon compounds are organic. What about elemental carbon? Well, did you know that both graphite and, like the graphite in your pencil, and diamond, you all know what a diamond is, those are both elemental carbon. Wow, they're really different, aren't they? We call graphite and diamond allotropes of carbon. An allotrope is simply a different molecular structure of the same element. Let's take a look at these allotropes of carbon. Graphite is found in your pencils. It's also used as a lubricant, and some of the reason is the structure of the allotrope itself. You can see here each of these dots represents a carbon atom. And each carbon atom you can see in this structure is bonded to 3 other carbon atoms. You know that there are 4 electrons. What's that 4th electron doing? Instead of bonding, it is with another carbon directly. That 4th electron is weakly bonded to the next layer above it. These layers are what allow the graphite to slide past each other. That's what makes it a good lubricant. Diamond, right here, is transparent and extremely hard. What makes it that way? Well, you can see that in this structure, this molecular structure, each carbon atom is bonded to 4 other carbon atoms in what we call a tetrahedron shape. These tetrahedrons are all joined together in this giant molecule where the atoms are held very tightly in a strong crystalline structure. That's what accounts for the hardness of diamond. And that brings us to this lovely little allotrope of carbon called informally a buckyball. Its real name is Buckminster fullerens. It's named after a man named R. Buckminster Fuller, who designed buildings that had similar shapes to this allotrope of carbon. And you can see how the carbon is arranged in a buckyball. It was discovered in the 1980s and kind of a soccer ball shape. It currently doesn't have any uses, but someday potential uses would be to make stronger building materials or make faster, smaller computers. In 1991, scientists were able to use buckyballs to synthesize really tiny, thin, graphite-like tubes. And we call those tubes nanotubes. Here's an incredibly close-up magnification of these nanotubes, and they're about 1/1000th of a meter in diameter. So what about the other elements in the carbon group? We have silicon. It's a metalloid that is incredibly abundant in the Earth's crust. Almost all rocks and soil have silicon in them. There are 2 allotropes of silicon. One's hard and gray, the other's a brown powder. Silicon is used, it's the main component in semiconductors. Those are elements that conduct an electric current under certain conditions. Most of your electronics use semiconductors to run. Germanium is also used to make semiconductors. We have tin and lead. Those are metals. Tin is combined with other metals to make bronze and pewter, for example. Lead used to be used a lot in paint, but it's very toxic, so it's no longer used in paint. It's used in car batteries, though. Let's take a look at the nitrogen group. Nitrogen and phosphorus are nonmetals. Nitrogen is found in a lot of different compounds like ammonia, nitrates, so fertilizers. Nitrogen is the 4th most abundant element in your body. Nitrogen also is a necessary component for amino acids, which make up proteins. Phosphorus is a nonmetal with 3 allotropes. It has a lot of different uses, from fertilizers to softeners. Phosphorus compounds are even found in match heads. Then we have arsenic and antimony. They are metalloids. Bismuth is a metal. Antimony here and bismuth are used in conjunction with other metals to lower their melting points. And because of that property, bismuth is used in automatic fire sprinkler heads, like this one. It lowers the bismuth lowers the melting point of the metal so that water will be released in the event of a fire. Now let's look at the oxygen group. Right here on the periodic table, oxygen, here's a close-up of it. Oxygen is a diatomic molecule. It's a nonmetal. Here we have our 3 nonmetals at the top of this group. Because it's diatomic, it goes around like this as 2 together. Oxygen is found in so many different compounds. Nearly all living things on Earth, including us, need oxygen for respiration. But oxygen is found in water. It's found in this molecule, hydrogen peroxide. It's also found in carbon dioxide. We have sulfur as the second element in this group. It's a nonmetal, several allotropes. Sulfur can be combined with metals to form sulfides with very distinctive colors, and those can be used as pigments in paint. We have selenium here. It's a nonmetal. It's necessary in very trace amounts in your diet. You can get those in multivitamins sometimes. You see that as an ingredient, but it can be very toxic if you get too much. We have the last 2 elements are metalloids, tellurium and polonium. Last, let's take a look at the synthetic elements. You know that elements that have more than 92 protons are kind of special. As a matter of fact, we call them transuranium elements. Uranium has 92 protons, and here I've put a box around those that have more than 92 protons, would be all of these and these elements, called transuranium elements, and they are very, very unstable. By 1935, there were only 4 elements that were not transuranium elements that were missing from the periodic table. One of them was francium, right here. That was discovered in 1939. But the other ones were technetium, element number 43. This was an element that was created synthetically. It was the very first created in a lab. Scientists smashed existing elements with particles that were accelerated in a very heavy ion accelerator, and they were able to create technetium. Just a year later, in 1940, astatine was created in the lab in a similar way, and then it was later found in very, very small amounts naturally. Promethium was the last missing element synthesized in 1947. So to give you an idea about instability with some of these elements, if we bombard uranium here with neutrons, we can make neptunium right here. And half of those synthesized neptunium atoms will disintegrate in about 2 days. Might not sound very useful, but when neptunium atoms disintegrate, they form plutonium right there. And plutonium is useful in nuclear reactors and in bombs. It can also be changed into the next element, number 95, americium. Americium is used in house smoke detectors. Synthetic elements can also be very useful because they're radioactive and ideal for different medical applications. Here is a picture of americium right there. You might think that it's sort of silly to make different things that are going to fall apart really fast. Nuclear scientists actually synthesize atoms that last for only fractions of a second after they're constructed, and they only make very tiny amounts of them. What's useful about that? Well, by studying how these synthesized elements form and disintegrate, scientists gain a much better understanding of the different forces that are holding the nucleus together. So finding large, stable synthetic elements might help scientists understand how the forces inside the atom actually work. Here are a few advanced ideas. Research the life and work of Marie Curie and her husband Pierre Curie, their contributions to chemistry. Find out why scientists add small amounts of gallium and arsenic to silicon. Ask your own questions. Anything interesting you would like to research at all that has been looked at. There is a lot that you could look at. I look forward to seeing your ideas, and we'll see you in class.